Hello everyone. I made this video to explain to you the different types of reversible inhibition and how to calculate Km and Vmax for each type and how the Km and Vmax values change. So first of all, before we get into inhibitors, the model that we're using is the Michaelis-Menten model where enzyme binds to substrate reversibly to form the enzyme-substrate complex. And then the substrate is converted to product and the enzyme is regenerated, as all good catalysts are. And what they found is that if you plot velocity versus substrate concentration, you get a hyperbola. So the velocity reaches a maximal velocity when all of the enzymes have substrate bound and all active sites are occupied. Whereas down here, the velocity increases with increasing substrate concentration because not all of the enzymes have substrate bound. So here what we're doing is we're assuming that we have a constant amount of enzyme and we're varying the substrate. So you can use curve fitting data program to fit the data to a hyperbola, and that's what we're going to do in lab. The curve fitting program will calculate the asymptote of this curve, which is the Vmax. 1/2 the Vmax is the Km. So the Km is defined as that substrate concentration at which the velocity is 1/2 the maximal velocity. So back in the olden days when curve fitting software was not as readily available, but you could get a piece of graph paper and a pencil and you could plot a straight line, people used to make these Lineweaver-Burk plots. So you take the Michaelis-Menten equation and then you take its reciprocal and you get y equals mx plus b, where the y-intercept is 1 over Vmax, the slope is Km over Vmax, and if you solve for the x-intercept minus b over m, it turns out to be minus 1 over Km. So you plot not velocity versus substrate concentration, but 1 over the velocity and 1 over the substrate concentration. And you get a straight line. So what you do is these are your points right here, and what you do is you extrapolate back to the x-intercept. So the y-intercept will give you 1 over Vmax. So if you want to solve for Vmax, you just take the reciprocal of the y-intercept. And if you want to solve for the Km, you take the negative reciprocal of the x-intercept. Because remember, Km has units of substrate concentration, so it cannot be negative. So the reason that we don't like to use Lineweaver-Burk plots that much is because you have a lot of error up here at really low substrate concentrations, but you still will see them in the literature. So we have to know how to do it. So now for types of inhibition. Competitive inhibition. Competitive inhibitors structurally resemble the substrate, and because of that, they can compete for binding to the enzyme's active site. So if the substrate gets there first, you form product. If the inhibitor gets there first, you don't get any product. So the substrate and the inhibitor look similar, but the inhibitor, even though it looks similar to the substrate, doesn't go on to form product. So we can take our Michaelis-Menten equation and modify it this way. Either the enzyme binds the substrate or it binds the inhibitor. So again, the substrate and the inhibitor are competing for the active site. So you either get an enzyme-substrate complex and you form product, or you get an enzyme-inhibitor complex, and since the inhibitor is occupying the active site, the substrate can't, and you get no reaction. So what happens to your Lineweaver-Burk plot is you get something that looks like this. If the green line right here is without the inhibitor, with the inhibitor, you get this red line. And the Vmax stays the same. And that's because, if I look at the Michaelis-Menten curve, that at high substrate concentration, the substrate will win the competition, even in the presence of the inhibitor. So if you have the substrate concentration high enough, you can actually get to Vmax. So that's why the y-intercept doesn't change, because you can get to Vmax if you have high enough substrate concentration. But the Km goes up. So again, remember the Km is this is the reciprocal. So that means if the minus 1 over Km goes down, that means that Km goes up. So the Km goes up, and you can tell by looking at the Michaelis plot, because the, again, if this is the Vmax, 1/2 Vmax, draw a line over, drop a line down, that's the Km with the inhibitor. It's going to take a whole lot more substrate concentration to get to Vmax when you have an inhibitor around. Okay, what about uncompetitive inhibition? The uncompetitive inhibitor doesn't bind to the active site. It binds only to the enzyme substrate complex. So what happens, there's an order where the substrate binds first and then the uncompetitive inhibitor binds. But when the uncompetitive inhibitor binds, it doesn't bind to the active site, it binds somewhere else, but it deforms the active site. So even though substrate's bound, the reaction cannot occur. So if we again modify our Michaelis-Menten plot or equation right here, the enzyme binds to the substrate, and if the substrate manages to get converted to product without the inhibitor binding first, you get product. But if the inhibitor binds, you get an enzyme substrate inhibitor complex, and again you're deforming the active site, so you get no reaction. And the Lineweaver-Burke plot looks like this. So and we can see why if we look, I don't have a great Michaelis plot. This is the best I could find. So, and their 1/2s don't even look that great. But anyway, what's shown in black is the Michaelis curve. So we have Vmax and then 1/2 Vmax. In the presence of the inhibitor, the Vmax can't be achieved because the inhibitor, since it's binding not to the active site but somewhere else, the Vmax is going to go down. And because the Vmax goes down, if you do 1/2 Vmax, then the Km goes down too. So what happens is Km goes down and Vmax goes down, and they go down to the same extent. So that's why the slopes are the same, because slope is Km over Vmax. So if Km goes down and Vmax goes down and they go down to the same extent, then the slope is going to be the same. But you can see that this light green, or I guess olive green curve right here is without the inhibitor. When you add lots of inhibitor, the 1 over Vmax is going up because Vmax goes down. Remember, we're talking about reciprocals. And the minus 1 over Km is going up. And again, it's a reciprocal, so the Km is going down. What about non-competitive inhibition? So, these names can be a little difficult, uncompetitive and non-competitive. But non-competitive inhibitor binds either to the enzyme or to the enzyme substrate complex. It can bind to both, and it doesn't matter which one binds first. So the substrate can bind, and then the inhibitor can bind second, or the inhibitor binds first and the substrate binds second. But if the inhibitor binds, and again, this one doesn't bind to the active site, it binds somewhere else, and it's not really shown very well in this figure, but the active site is deformed, so the substrate can't form product. So here, for non-competitive inhibition, the enzyme can bind substrate first, and then the inhibitor can bind, forming this enzyme substrate inhibitor complex. Or the inhibitor can bind first, and then the substrate can bind second, and you get the enzyme substrate inhibitor complex. Either way, if you get an enzyme substrate inhibitor complex, you don't get product because the inhibitor is deforming the active site. So these are the Ki values. We're not going to go into the Ki values with this video, so I'll describe that at another time. Okay, so the wrinkle we have here with this non-competitive inhibition is that you have a scenario with, since the inhibitor binds to the enzyme and it binds to the enzyme substrate complex, it's possible that the inhibitor binds to the enzyme with greater affinity than it does to the enzyme substrate complex. So if that happens, you get something that looks like this, where if you look at the Michaelis curve, this is without the inhibitor, and then with the inhibitor, again, you don't get to Vmax. And here, again, if you go that 1/2 of the Vmax, drop a line over, drop a line down, you can see in this scenario the Km goes up. So the Vmax goes down and the Km goes up. And what will happen is the appearance of your plot is that the two lines will intersect above the x-axis. But again, if we can see this without the inhibitor, if you look at with the inhibitor, the y-intercept goes up. That means Vmax goes down because it's the reciprocal. And again, if you look at this purple line right here, and again, since this is a Km, which is in the reciprocal, so here, this means that the Km is going up because the negative, the x-intercept went down. So the Km is going up. And that's what you get if the inhibitor binds to the enzyme with a greater affinity than it does to the enzyme substrate complex. I couldn't find this, so I had to draw this myself. It is also possible that the inhibitor binds to the enzyme substrate complex with greater affinity than to the enzyme. And what happens here is that the Vmax will still go down. Again, if this is no inhibitor and this is with inhibitor, the Vmax is going down because this is a reciprocal, so this goes up. So here with no inhibitor, you can see what's happening here is that the x-intercept is going up. That means the Km is going down. So here both Vmax and Km go down, but not necessarily to the same extent. Or it's possible that the inhibitor doesn't care, that it binds to the enzyme and the enzyme substrate complex with equal affinity. And if that happens, the Km stays the same. So the Vmax is going to go down because the y-intercept went up and it's reciprocal, but the Km stay the same, so the x-intercept is going to be the same. So, to summarize, if we look at the Michaelis-Menten equation and the Lively-Roberts equation, and they have these factors called alpha and alpha prime, so we will not worry about those right now. But this is the Michaelis-Menten equation, this is the Lively-Roberts equation. For competitive inhibition, the Vmax stays the same. So if you look at this at the y-intercept, there's no change. The Vmax stays the same, but the Km goes up. For uncompetitive inhibition, both the Km and the Vmax go down, and they go down to the same extent. It's obvious here, I think, that the Vmax is going down because we have this term right here. It's not as obvious over here because there's actually an alpha prime term here and an alpha prime term here, and they cancel out. But what we do see is that the slope doesn't change. The slopes are the same. And for non-competitive, and to make it even more difficult, sometimes it's called mixed, the Vmax goes down in all three cases, but the Km might go up or the Km might go down, and what's not shown here is the Km might stay the same. It depends on whether the inhibitor likes the enzyme substrate complex more, does it like the enzyme more, or does it not care. In all cases, what you do, to remind you, is when you're trying to solve for Vmax, remember the y-intercept is the reciprocal. So 1 over the Vmax is the y-intercept. So just take the y-intercept, flip it, and you've got the Vmax. And for the Km, it's the x-intercept. So look at the x-intercept, flip it, and change the sign, and you have the Km. So this is going to be true either with or without the inhibitor. So if given a graph, you should be able to solve for Vmax with and without the inhibitor, and Km with and without the inhibitor. So I hope this is helpful. Thank you for your attention, and see you in class.